So today we're going to look at lesson 2-1, which is all about relations and functions and their graphs. So let me move this over a smidge. Let's talk about our vocabulary first. So first, a relation is just a set of pairs of inputs and outputs, or output values. And essentially, really what a relation is, it's just a set of ordered pairs. I have got to get me a new stylus. I keep saying that one of these days. Okay, now there are 4 ways to represent a relation. The first way you see here is just a set of ordered pairs, and that's what I said a relation is. We can take this set of ordered pairs and make what's called a mapping, a table of values, and a graph. So I'm going to do that for the same set of ordered pairs. So our mapping is going to be one oval and then a second oval. Looks like a pair of lungs. And then this is going to be our x values, and this is going to be our y values. So essentially this is our input, and this is our output. Inside the oval, we are going to take for our x values, and we're going to take all of these x values here and list them in order from smallest to largest, and we are not going to repeat any values. So here our smallest x value is -3, then 3, and then 4. We're not going to repeat this 4. So a -3, 3, and 4. So smallest to largest, don't repeat any values. Then over here we're going to put our y values. So our y values are 4, -1, and 3. The smallest being -1, 3, and then 4, and we're not repeating those negative ones. So -1, and then 3, and then 4. Then we need to write arrows, and essentially the rays, a ray is an arrow or a line with an arrow on one side. So you're going to go from the input, which is your x, and go to its respective output. So because -3 maps onto 4, -3 maps onto 4, we're going to draw an arrow from -3 to 4. If you just draw your line like this, I'm going to mark you wrong. You've got to have an arrow on that right-hand side. So that's an ugly arrow, but it is. And then our next ordered pair is 3 maps onto -1. So I'm going to go from 3 to -1. Then our third order pair is 4 to -1. So we have 2 arrows going to -1. That's okay. We're going to talk about what makes a relation a function in a minute. And then finally, our last ordered pair, 4, 3, we are going to go from 4 to 3. So we actually have 2 arrows leaving 4. Then we're going to do a table of values. So a table of values is just an XY table. Essentially, it looks just like this ordered pair, but we're putting it in an XY table. So here's your X and Y. And this can go horizontally as well. And then we're just going to put each of these ordered pairs here. You don't want this table of values to go from smallest to largest because you want your ordered pairs to match up. So -3 matches up with 4, and then 3 matches up with -1, 4 matches up with -1, and 4 matches up with 3. Then let's look at a graph. So I'm going to create a coordinate grid. I'm going to do a 5 by 5. Well, I can only get 4 there. That's good enough. Okay. Then I am going to graph these ordered pairs here. Remember your x values, this is going to be your x-axis, and this is your y-axis. It is understood that you know that. And then your x value goes in a right-left direction. So if it's negative, negative is to the left, positive is to the right. Your y value goes in an up-down direction. So if it's positive, that's going to go up, negative is going to go down. So if I plot 3, -4, or -3, 4, I'm going to go to the left 3 and up 4. So about right there. And then 3 and -1, I'm going to go right 3 and down 1. And then 4, -1, I'm going to go right 4 and down 1. So those are next to each other. And then 4, 3, I'm going to go right 4 and up 1, 2, 3, kind of about there. Okay, so we're going to leave that for a minute, and we're going to talk about domain, range, and function. So let's look at the values for these. So for the domain, and you might recall this from Algebra 1-2, the domain is the set of all x values and it is the x coordinate of the ordered pair. And essentially, this is going to be our input. So x values are your input. Then the range is the set of all y values which means that's the y coordinate of the ordered pairs of a relation. And this is our output. Okay, so we've talked about domain and range. If you have trouble figuring out, if domain is the x values or the y values and vice versa, I'm not big on memorization, but here's an easy way to remember it. Doesn't x come first alphabetically between x and y? So the answer to that's yes. And alphabetically, doesn't domain come before range? So that means that if domain is alphabetical, it matches up with x, the alphabetical order of x and y. And then range and y are going to match up. So think alphabetizing. X goes with y, and then domain to range. So x, y, domain, range, meaning the domain is your x values, and the range are your y values. Then finally, a function. So here's your technical definition of a function. So a function is a relation. Now remember, not all relations are functions, but all functions are a relation. So that's why this says a relation in which every element of the domain corresponds with exactly one element from the range. And what this implies is that x values, so this is in simple terms, x values do not repeat. That's what that means in simplistic terms. X values do not repeat. So then we're going to look at down here all the rules for determining if a relation is a function. So remember, we looked at all of these are different types of functions that you can have. We're going to look at the rules that you need to apply to each of these functions, and then we're going to apply them to the functions or the relations above that we drew. So if you have a set of ordered pairs, you want to ask yourself, do the x values repeat? There's only two tests that you're going to apply. So let's go up to the ordered pairs and let's look at this. Look at only your x values. Notice how 4 and 4 repeat. So I'm going to put a circle around the 4s, and I'm going to write not a function. Not a function. I'm going to squeeze it in there, not a function. And the reason are the x value of 4 repeats. Now, I'm probably not going to be able to write this on the others because I have very little room left up there. But you might want to put an arrow from this down here all the way up to these ones up here. All right, so then the next one is in a mapping. So as you look at a mapping, we also want to ask the question, do the x values repeat? This one's not as easy to determine if the x values repeat. So remember, you're looking to see is there more than one arrow? I'll move this up a little bit. Leaving an x value. Because if there's more than one arrow that's leaving an x value, that must mean that the x value repeats. So look up here at this mapping. Notice that here we see two arrows right here. Here's an arrow going to 3 and an arrow going to -1. Two arrows are leaving 4. That implies right here that the x value of 4 repeats. All right, let's look at in table of values. So table of values is again the same rule. Do the x values repeat? And so the table of values is pretty simple to see if those x values repeat, because unlike the mapping, it's going to actually show that. So circle these, because this is not a function, because the x value of 4 is repeating. All right, let's look at our table of values. So, or I'm sorry, our graph. So the graph is going to actually use this vertical line test. Well, what does that mean? And remember that a vertical line is going to go north and south. If you don't remember what a vertical line is, it's north and south. And so you're looking to lay that vertical line anywhere across the graph, and you're trying to determine, is the graph touching that vertical line more than once? So that's the question you're asking yourself. Does the graph touch the vertical line? I'm going to abbreviate it as vert line more than once. Okay, so let's test that up here. Let's go through this graph. I'm going to apply the vertical line test. So if I apply the vertical line test right through here, there's a vertical line, it only touches the graph once. So far, so good. If I feel like I forgot a point. We have 1, 2, 3, 4, 1. No, we didn't. So here's a vertical line through here, touches the graph only once. But now look at this vertical line. Doesn't it touch 2 points? The 2 points it touches are here and here. So that does not pass the vertical line test. So this is not a function, and you don't have to test whether it's a function on all 4 representations of a relation. You just need to have one representation, and it needs to fail. If it fails one test, x values repeat, then it's going to fail the other test. It doesn't pass the vertical line test. All right, so let's look at some more examples. So for this one, you have a set of ordered pairs here and here. So the only time I can apply the vertical line test is if there's an actual graph. So unless you're going to graph these, you can't apply the vertical line test. So let's go ahead and separate this out into the domain and range. And when you separate it out into the domain and range, it's kind of like what we did with the mappings. You want to write your domain and range in numerical order, small to large, and you don't want to repeat anything. So look at your domain here. So I've got -2, 0, 4, and 5. So my smallest domain, and we are going to use these things called braces. I just drew one of these things, which, as you can see, I'm a terrible artist, but that's what that is, just in case you were wondering. Okay, so your domain, your smallest domain value is -2, and then your next smallest is 0, then comes 4, and then comes 5. So none of the x values repeated here, which actually should answer the question, is this a function? Yes. And your reasoning is x values do not, that's terrible, do not repeat. All right, so let's do our range. So our range values are here, 0.5, 2.5, 6.5, 2.5. So we're going to use braces again. Our lowest range value is 0.5. So I'm going to start there, comma. And then we have 2.5. We are not repeating that 2.5. You're just writing it once. And then finally 6.5. It is okay to repeat y values. It'll still be a function, but it is not okay to repeat an x value. So then what I want you to do is I want you to try B on your own. So pause the video, write out the domain and range, determine if it's a function, yes or no, and why or why not. Okay, so on part B, your domain is going to be 6, 4, 6, and 5. So your smallest, oh, that was a terrible one. Let's try that again. So there we go. So then your smallest is 4, and then 5, and then 6. And then we are not repeating the 6. So since the 6 repeats, I can automatically tell you it's not a function, and the reason is the x value of 6 repeats. That is your reasoning why it is not a function. And then your range is going to be the 5, the 3, the 4, and the 8. So your smallest is 3, then 4, then 5, and then 8. Okay? And now let's look at a mapping. So if we look at a mapping, mapping is pretty simple to find the domain and range because notice that they've already listed it from smallest to largest and they haven't repeated values, and same thing here. So for your domain, we're just going to simply write -3, 0, and 4. My braces are getting worse and worse. There. And then for your range, it is -2, 1, and 7. Now sometimes in your textbook or on programs like Math Excel, they will write the mappings incorrectly to try to trick you. So they'll not put these in order from smallest to largest, and they'll repeat values because they're trying to trick you. Just know that that's not the proper way to write a mapping, and they're doing it on purpose to try to trick you. Okay, so based upon this, you're going to determine if it's a function by looking at the arrows. There is only one arrow leaving each of these x's, so what that implies is that this is a function because the x values don't repeat. So x values do not repeat. Now, I want you to do part D. So pause the video and do part D. All right, so the domain on D is 2, 3, 4, and 6. And then the range is -3, -1, 3, and 6. then you're going to determine if it's a function by looking at the arrows. See how the arrow's right there? There's more than one arrow right here, leaving that 2. That implies that the 2 repeats. Since the 2 repeats, no, this is not a function because the x value of 2 repeats. All right, let's look at some graphs. So the first thing you need to do is plot your ordered pairs, right? So I want you to pause the video and plot these ordered pairs, and I want you to see if you can figure out the domain, figure out the range, and determine using the vertical line test, because it's a graph this time, so we're switching to that different test, if these are functions or not. Okay, so if I plot these ordered pairs, okay, I would have 4, 2 is right here, and then 1, 2 is here, 0, 1 is on the y-axis, not the x-axis, negative 2, 2, and 3, 3. So your domain is going to be your leftmost x value. This is the first point we come to on the left. Go down to the x-axis is negative 2. Or you can look at your ordered pairs like we did earlier, but I'm just looking on the graph. And then as I keep walking towards the right, this is the next point I come to, and go down to the x-axis. That's an x value of 0. And then the next point I come to is right here. That's an x value of 1. And then the next point I come to is right here, so that's an x value of 3. And then the final point that I come to is right here. The x value of that is 4. So that's your domain, then your range, or your y values. So start low and go high. So the lowest point that I come to is this one, and it's on the y-axis at 1. So that's your lowest y value is 1. Then the next points that I come to going from low to high are these 3 points right here. They're all on the same y level, and they all have a y value of 2. And then the topmost point is this one right here, and it has a y value of 3. Okay, let's apply our vertical line test. So if I draw a vertical line through this graph, all throughout the graph, notice it only touches the graph once. So far, once, just once, and just once. Nowhere does a vertical line touch this graph more than once. So because it only touches it once, we are going to say that yes, this is a function, and the reason is it passes. And I'm going to abbreviate this as VERT for vertical line test. Okay, so then for F, I'm going to plot those points. So 0, 2 is on the y-axis, 1, negative 1 is here, negative 1, 4 is up here, 0, negative 3 is on the y-axis, and 2, 1 is here. So again, your domain, your leftmost point is, as you walk in this direction, is this one right here. Go down to the y-axis, that's negative 1. Your next point are these 2 points from the left, and they go to the x-axis right here. That's an x value of 0. And then your next point is this one, and it has an x value of 1. And your final point is this one, and it has an x value of 2. Then your y values start from low and go high. So your lowest point is this one. It's on the y-axis at negative 3. Then your next value is this, or your next lowest point is this one. Go over to the y-axis. That's at negative 1. And again, you could use your ordered pairs to do this. Your next lowest point is this one. Go over to the y-axis is 1. Next lowest point is this one. It's on the y-axis at 2. And then your highest point is this one. Go over the y-axis and it's 4. Okay? Then we're going to apply the vertical line test. So here it just touches it once. But here I can stop because it is touching it twice. It touches it once here and once there. So it only needs one incident of where it doesn't work for it to not be a function. So this is not a function because it does not pass the vert line test. All right, so let's flip to the next page and look at some different types of graphs. These graphs are a little bit different because they're not just ordered pairs, they're actually continuous curves. And so there is not just a finite set of ordered pairs that I can write. There's an infinite number of ordered pairs on this line. So the question is, how are we going to write the domain? So remember, domain are your x values, and so domain goes from the left of the graph to the right of the graph. So to figure out the domain, you want to go all the way to the left, and because this graph is going down and to the left, how far to the left would I have to go without stopping? Well, I'm never going to stop because this graph continually goes down, but to the left, down and to the left, down and to the left. So since it goes to the left infinitely, we are going to write for our domain negative infinity, because to the left is a negative direction for x. And so we're going to do negative infinity, and then we're going to do a comma because we're going to go from negative infinity all the way to going to the right this time. If I go to the right, this graph continually goes to the right and up forever. So it's going to the right and up forever. Will I ever quit going to the right? Nope, it's going to keep going and going and going, which is infinity. This time it's a positive direction for infinity. And then we're going to write parentheses here because it means that our graph is going from negative infinity to positive infinity. Normally we put parentheses or brackets around here, and this is called set notation. I'm trying to get you to set notation. This part is new for you. So I'm going to talk more about whether these are parentheses or brackets on the graphs below these ones. But for right now, anytime you have infinity, we always put parentheses around infinity because we don't actually know what number infinity is. So then our range goes from low to high. So remember, this graph goes down and to the left forever. So it goes down and down and down and down and down forever. So that's in a negative direction. So for our range, we're going to do parentheses, negative infinity. And then we're going to go up and up and up. This goes up and up to the right forever. And because it's going up forever, up is a range direction, and so that's positive infinity. So those are your set notations, and what this means is that my domain is the set of all real numbers because it's from negative infinity to positive infinity, and same thing with the range. So let's write that in here as well. X is equal to all real numbers. And over here, y is equal to also all real numbers. Then we're going to apply the vertical line test. If I run a vertical line through this graph, no matter where I run it on this graph, I'm only ever touching the graph once. There is never one instance, not even one instance, that creates a situation where I'm touching the graph more than once. So because of that, this is indeed a function. So yes, it's a function. Reason it passes the vert line test. Remember, that's vertical line. Okay, you try H on your own. Try to figure out what the domain and range are here for H, and then if it's a function, yes or no, and then why or why not. So pause the video and do H. Okay, so for here on the range, so remember, or I'm sorry, for domain, we're going to go to the left. And because this graph continues and goes to the left forever and ever and ever and ever and ever, that is, again, just like the previous graph, that's going to be negative infinity. So we're going to put parentheses around that, negative infinity. And then this graph continues and goes to the right forever and ever and ever and ever and ever. And that is also infinity. So both of these graphs have the same domain. Then let's start low and go high. In other words, how low does this graph go? If it goes to the right, I know it's a little hard to see because that looks like it's horizontal, but it's really not. This graph is going to the right and it's going down slowly. So it might be a really slow slope down, but it's going to the right and down infinitely. So that's that right-hand side. The left-hand side, which is over here, notice that the left-hand side is going to the left and up infinitely. So the lowest value is negative infinity. To the highest value is positive infinity. So this has the same range as the other one. So both of these graphs have the same domain and range. And remember, this means y equals all real numbers. And then this one meant x equals, because x is domain, all real numbers. Okay, and then to determine whether this is a function or not, we are going to apply the vertical line test. So if I apply the line test here, it works. It only touches the graph once until I come, oopsies, it's touching the graph more than once now. So I'm going to actually put in a vertical line right close to this black line here. And you can see that it is touching this vertical line once, twice, 3 different times. So if it touches it more than once, then it is not a function. So that's no. And the reason being it does not pass the vertical line test. Okay. All right, so let's move this on to the 2 graphs below. These are 2 more different styles of graphs that you're going to see. So again, we're going to find domain and range. I'm going to move these up as best I can. So here we're going to talk about a little bit different set notation, because this is a different style of graph. As I go from left to right, because that's what my domain is, from my left, this is the leftmost portion of the graph right here. That's the left side of the graph. And if I go down to the x-axis, that value right there is -5. So the leftmost value of my graph is -5. We're going to talk about parentheses or brackets here in a minute. And I'm going to go to, and it's going to look like an ordered pair, but it's not. I'm going to go to the rightmost value. So we go from -5 to the right, and then the rightmost part of the graph stops right here. So that is the rightmost part of the graph. So the x value there is 3. So we have x values that go from -5 all the way to 3. And it's all on this circle. And I guess technically you could include that dot right there as well. But and a lot of kids would want to go, okay, well, why don't I just list it? If I go from -5 to +3, why don't I just list it as -5, -4, -3, -2, -1, 0, 1, 2, and 3? You can't just list the integers because this is a continuous graph here and up here. So what that means is there are points in between -5 and -4. There's actually an infinite number of points between there. There's an infinite number of points between all of these integers. So let's just look at like between 1 and 2. I could do 1.5, I could do 1.55, 1.555, 1.55555, 1.5555555. I mean, do you see where I'm coming from? I could do this all day long. So this implies that I'm going from -5 to 3, including -5 and 3 and anything in between. All right, so this also kind of looks like when we graphed something on the number line. So if I graphed something on the number line, I'm just going to do it for this one. I would have graphed it from -5 all the way to 3. Of course, I'd have some other points in there. I would have a closed circle at -5 because it includes -5 as a value, and I would have a closed circle at 3 and a line in between because I'm going from -5 to 3. So I want that notation there to represent this. So you might want to write over here that parentheses around a number is the same as open circles on the number line. It means that the graph comes close to that value but doesn't actually equal that value. If I have brackets, that's the same as closed circles on the number line. Okay, so because I want to include -5 and 3, we are going to use brackets because it represents these closed circles right here. So this represents this exact same thing on the number line. So the other way that you could write your domain is with inequalities. So domain is x. Whoops, let me get my pen here. So domain is x, so x, and then this part would be x is less than negative, or x is less than 3. So I'm going to write x is less than 3. And then since it's an and statement, I can sandwich it. Here, x is greater than -5. So from a sandwich statement, because we read it backwards, this means, I'm reading it backwards, x is greater than -5. So these are the two different ways that you could show your domain. I prefer this way because it's the way I'm trying to get you to go. We'll have to look to see what Math Excel does though. And then your range, remember your range goes from low to high. So isn't this your lowest point on the graph, and it goes to the y-axis here at -1, and the highest point is here at 7. So our range is going to go from -1 to 7. Because -1 and 7, and that's these points right here, include a y value of -1 and 7, they're included in our solutions. So we want to have brackets there because that would be like closed circles on a number line. And because we're dealing with y, we're going to say y, and then y would have to be less than -7 because we're going down, or less than +7. I don't know why I keep saying negative. And then y would have to be greater than -1 because we would be going up. So greater than, or equal to, my bad, -1. So that's what it would look like if you used inequalities. Now, let's determine if this is a function. So I'm going to use the vertical line test. Now, if I put the vertical line here, it passes. But remember, I just have to have one instance. So I'm going to put the vertical line through here. And now you can see that it doesn't pass because it's hitting our graph here, here, and here. That's more than one spot. So because of that, no, this is not a function. It does not pass the vert line test. Now, you do J on your own over here. Pause the video and you try to do J on your own. Okay, so if we look at this graph, for my domain, I want to go to the left, and notice that the graph is going to the left forever because it's going up and to the left forever. So remember, forever is going to be -infinity, and we always use parentheses around infinity because we don't know exactly what number that is, so we can't say it's here and put a bracket. And then to the right, we're going up and to the right forever. So because the right is forever, that's a positive infinity. And then your range starts from low to high. Well, your lowest part of the graph is right here. At that point, the y value is 0, and 0 is included on this graph because this ordered pair is 0, 0. So that means we put a bracket here, and then the graph goes up infinitely forever, and so that would be positive infinity. And of course, you put a parentheses around infinity. Now remember, this domain here means that x is equal to all real numbers, And this range means that y, now if you think about it, I'm going to have a closed circle at 0. Think of the number line. Closed circle at 0, and I'm going to go to the right to infinity. So that would be a closed circle at 0 and an arrow to the right forever. So that means that y is greater than or equal to 0. We want to determine if this is a function. If I put a vertical line anywhere through this graph, it never touches the graph more than once. So that means the answer to that is yes, it's a function, and reason being, I'm going to move this up a smidge, it passes the vert line test. Okay, on this last page, we're going to talk about what is a function rule, what's function notation, and independent and dependent variables. And so, for a function rule, it's just an equation that represents an output value in terms of an input value. In other words, if our input value is x, it's an equation that's in terms of x. So an example of that might be y equals x plus 8. Then we're going to get fancy and put it in what's called function notation. So function notation is just a way of writing a function rule. Here's your function rule. It's a different way of writing that function rule. And essentially, we replace the output value, which is y, with the function notation. And function notation is usually this f of x. It's read f of x. It can be f of x, g of x, h of x, t of x. It can be any letter of the alphabet. The most popular one is f of x. So I'm just going to rewrite this rule in function notation. I'm essentially going to rewrite this y right here as f of x equals x plus 8. It's the same function rule, just written in function notation. So then x is considered our input value. So x is your input value. And then here, the whole f of x, so I'm going to put that in a different color. So from f to x, that's your output. All right, so because remember, f of x is the same as y. So your independent variable is your input value of x. Your dependent variable is your output, which is f of x, which is y. And I also put here, it's called dependent because it depends on the value of the independent variable, which is your input. So if you know your input, you'll be able to find your output, which is your dependent. All right, so let's apply these. So you're going to use function notation to find the outputs of this function. So essentially, you've got 3 different outputs and 1 function rule. You are essentially doing 3 problems in one. So if this is my function rule, x, these are my x values. We're going to put each one of these values in for x. This does not mean f times x. Remember, it's f of x. Basically, it's calling this function, giving it a name of f, and it's saying for every x, whatever you put in here, like let's say I replace the x with a -3. So it would look like this. F of, and then I'm going to replace every x with what our first input value is. So if our first input value is -3, wherever I see an x, I'm going to put in -3. And what this is saying is in the f function, wherever you see an x, put a -3. So I only have one x, so I only put in one value of -3. And then we're just going to do the math. So -2 times -3 is +6, plus 5 is 11. So f of -3 is 11. Essentially, your input is -3, your output is 11. So f of -3, your y value, is 11. This actually creates an ordered pair of -3, they didn't ask for it, 11, but I'm going to write it here. All right, then you're going to do that 2 more times. So pause the video, and I want you to use the input of 0, put it in just like this, and then the input of 1/4. And then start the video and check your answer. Okay, so I'm going to put in 0 in for the second input. So I'm subbing in 0 for every x. So the -2 times 0 is 0 plus 5, and 0 plus 5 is 5. So f of 0 is equal to 5. If I was asked to write that as an ordered pair, it would just be 0, 5. Okay, and then finally, you should have done f of 1/4. All right, so we're going to put in for x 1/4, and then every x in our rule, we'll replace it with 1/4. So -2 times 1/4, you can either use your math or your calculator, is going to come out to be -1/2 plus 5, which is 4 and 1/2, which is 9/2. So I prefer the improper fully reduced fraction, 9/2, and so f of 1/4, and again you can use your calculator to help you with that. So if you had to write an ordered pair, the x value would be 1/4, the y value 9/2. Okay, so it's just input-output rule. Then you might have some word problems, and so this is our last problem. You have tickets to a concert. They're available online for $35 each plus a handling fee of $2.50. Boy, is that cheap. The total cost is a function of the number of tickets bought. So the total cost is a function of what? If I knew the number of tickets bought, I could find my total cost. So your independent variable is the number of tickets bought. So independent is going to be the number of tickets bought. So we are going to let x equal number of tickets bought. Okay, so then your dependent variable is the total cost is a function of. So that's kind of code for that function notation. So your dependent variable is your total cost, and that's going to be c of x, right? Which is your y, right? C of x, which is your y. Your dependent variable, that's your y, and so we're going to write it instead of y equals, we're going to write it as c of x. So then they want you to write a function that models the cost of the concert tickets. So I would be able to figure out the total cost if I had $35 each. So wouldn't it be x times 35, number of tickets bought, times $35, and then add a handling fee of $2.50. So that looks like, let's see, c of x, our total cost, is equal to $35 times each ticket, so times x, and then plus $2.50. So there is our function notation. Then we need to evaluate the function for 4 tickets sold. So isn't 4 tickets sold a independent variable? This is our x, right? So we're going to take c of, I'm going to rewrite it with parentheses. And instead of x, we're going to replace x with 4. So every x in the rule needs to be replaced with 4. So there's only 1 here. So then I get equals 35 times 4 is 140 plus 250. So that means c of 4 is equal to 142.50. Right, and that's in dollars. And then you're to evaluate the function for 200 tickets sold. So I want you to pause the video. I want you to evaluate the function just as I did before, and then restart the video and check your answer. So I'm going to do c of Okay, instead of X, they're wanting us to put in 200. So it's C of 200. So everywhere I have an X in the rule, I must replace it with 200. Then I'm pretty sure you're going to want to use your calculator for this, but 35 times 200 is 7,000 plus $2.50. So therefore, C of 200 is equal to 7,002.50, and that's in dollars. That's your total cost. And that's it. So try your homework. If you have any questions, please don't hesitate to text me. Have a good day.